All right, next up is Tom Scholl with jumbo packets on the internet.
Hi, my name is Tom Scholl with AT&T, and this talk is just going to be about jumbo packets on the internet, basically increasing the MTU that you can expect on the internet. Just a quick review of some of the acronyms obviously going to be used here. MTU, maximum transmission unit, obviously is the largest size packet or frame possible on a link. Path MTU Discovery, a host-based mechanism to discover the end-to-end maximum MTU to an individual destination. So one of the things is, what is the maximum MTU that you can expect really on the internet? And obviously it depends. Different technologies have different default MTUs that are configured. HISI, FIDI, Packet over Sonnet, ATM all support 4470. Ethernet, on the other hand, by default is typically at, standard is at 1500. One of the things is that Ethernet is pretty common access technology on the edge, but it's also very popular in the core too as well. But this being set at 1500 kind of renders any kind of large frames a little bit useless. Now, and then there's other issues with as it relates to Path MTU Discovery, and they'll be discussed later on in the presentation. But it has its own issues as well. So this slide actually Richard Steenburgen helped a little bit about. So some of the information here can be a bit accurate, some of it not so much. Basically, one of the things is you can look at it as bigger packets equals fewer packets per second, which is good for routers because it's fewer lookups that you have to do, fewer interrupts. One of the things is how beneficial is this really on the host side, where you do memory copies and things like that. Clearly, bigger packets work, but on modern equipment, it can be debated how well, how beneficial this might actually be. One of the things is with jumbo frames, what exactly is a jumbo frame? So there's really no standard. Basically, it's anything larger than 1,500 bytes, but there is no actual stated standard right now. 1,500 has been the way that it's has been for quite a while, but in the last several years, any kind of modern hardware vendor has offered the ability to increase MTU on any given interface. So modern equipment can do larger than 1,500, and this is really driven by customers and not really any kind of standard that was driving it. And obviously, there is no standardization on anything above 1,500. So what value to specify or use is entirely up to the operator. Path MTU Discovery, one of the things discussed here is it's there to prevent fragmentation within the middle of a network in the path. Fragmentation is somewhat difficult on routers because typically if a packet has to be fragmented, if it doesn't have don't fragment set on it, it's maybe punted to a route processor or line card CPU. Basically in the end it's taking the slow path to get there because it has to be fragmented on an intermediate device. So the way Path MTU Discovery works is hosts send out a packet with don't fragment set. If the Path MTU is too small, the router will send an ICMP message back to the original host instructing it that it wasn't able to get there, and the host at that point will readjust the packet sizes. There's some issues with Path MTU Discovery though, because it is somewhat easy to break it. And specifically one of them is ICMP, if the unreachable message, type 3 code 4 I believe, goes back to the original host. If it's not ever received, Path MTU kind of breaks in that scenario. Common thing was for several years, a lot of people filtered ICMP to their network, all ICMP messages or just unreachables, and in this case, this obviously led to some problems here. Another thing is what happens if somewhere in the middle of the path of a network between two links they have mismatched MTU. In that case, the ICMP message would never get transmitted back because one side would assume that it had its MTU negotiation was okay. And if Path MTU Discovery breaks, you essentially have a traffic black hole in that scenario, which could last potentially forever. So just a graphical picture of why is Path MTU mismatch a bit fatal. Here we have host A sending a packet all the way to host B in this case. And the MTU on router A is configured for something around 9,000. The MTU on router B is configured for 1,500. They have a mismatch. Router A sends out the frame. It's too large for router B. It obviously doesn't get to its destination. Router A is unaware of this. The ICMP message never gets sent back to host A, and so host A is oblivious to really what's going on. So within any kind of network that anyone's operating, setting MTU standards are pretty trivial because you control all your own equipment. You can actually set these standards and agree upon something. It's pretty consistent when you run your own organization, and you can do these things. Inter-provider, it's a whole other story altogether. Depending on what kind of links you're using, it varies in what kind of difficulty you might run into. On point-to-point links, it's fairly easy because essentially you can ask, let's say, the pair or whomever, let's agree upon an MTU and implement it. That works great. That, as long as you go out through some of the intricacies that I'll talk about later on. One of the other problems is what do you do on a multi-point link, though? So point-to-multi-point, like if it's a internet exchange, VLAN, pairing fabric, anything like that, it's a bit more complex because you can't just set a higher MTU because not all participants are going to support it in some cases. So you run into problems where you can't just go into an internet exchange and set something higher. Typically, everyone talks at 1,500. So there's really no way as a router on any of these point-to-multi-point links that you can actually do to negotiate the MTU to any specific neighbor. That mechanism does not exist today. However, a lot of the modern routers today actually have the ability to track per next hop or per neighbor MTU sizes. So the hardware today that we're already deploying can actually do that internally. The only thing that's really missing is the ability to negotiate it with an individual neighbor on that LAN. So one thing is, how can you really fix this? Well, there's a few different options. One of them is, what would appear to be a proper way to do this would be using ARP. One of the ideas here would be perhaps something like an adaptive ARP protocol where basically you would use ARP probing to, alongside the existing ARPs that would go out to a destination host or router on a LAN, you'd use the existing ARP to find out its MAC address, and then afterwards perhaps you could send a subsequent message which would be a padded ARP to whatever size, and then you can scale up from there. And then at that point you could try to do some sort of discovery mechanism based upon that. So that would be one interesting thing to do, but however, the question is who's going to implement it, how does it get standardized? But it seems like if this was going to be done anywhere to negotiate a MTU, that ARP would probably be one of the best places to do this. Another place you could possibly say would be, well, using BGP and advertise a capability. I mean, it's BGP, you can throw a lot of different things into it. This could be one of them. The only problem there is obviously you need to run BGP. There may be scenarios where you may not have BGP running on a particular LAN and you have no desire to do so. So you probably don't want to lock yourself into BGP in that case. The other one would be picking a number and just hoping everybody supports it, which doesn't exactly work, or hopefully there's some sort of consensus among members on a LAN that they'll operate with a specific MTU, but how enforceable is that, or how much will people actually adhere to something like this? Some internet exchanges have gone the route of doing actually separate VLANs. In this case, for jumbos, I believe NetNod has actually have a separate one on the side for larger MTUs. But that kind of brings up a question of how feasible is that really? Because right now there's different exchanges, and you already have an IPv4 or an IPv6 or a multicast or whatever else VLAN that's set up. If all of a sudden you said to support jumbos, we're going to set up a separate VLAN. Do you really want to maintain all that, or would you rather just find a way to do it on whatever you have existing? So one question is really what MTU value would you even want to support? So one thing is, well, certainly something above 1,500 would be nice. But since jumbos in general, when people refer to them, they're talking around somewhere around the 9,000 range. So something around 8,000 to 9,000, maybe 8192 for whatever will be the underlying data payload, and then plus additional padding or extra room for whatever type of encapsulation. And that would be for whether that be multiple layers of IP or MPLS or whatever kind of encapsulation of tunneling that you'd want to support, so that you can have a clean MTU that could be delivered end to end. Anything really is better than 1,500 at this point. I mean, right now it's a lot of the internet exchanges. Sometimes people are coming there on different transport. They can't get 1,500. It's something far lower in the end that you end up communicating with. And there are the options to support certainly larger than 8,000. Obviously 65,000 and whatnot, but there gets into other issues of how well the CRC works for error correction. Some other issues with actually implementing larger MTUs, specifically how do you actually specify the MTU on an interface? And this varies from vendor to vendor, even in the same vendor on different operating systems that the vendor operates. When you specify MTU, what does that really mean? Does it mean the actual frame payload that you're delivering? Does it actually mean the frame plus headers? Does it mean the frame plus headers plus FCS? It's really not clear on each vendor. Every vendor does it their own particular way. And, and at the same time, what about VLAN, the 802.1q tagging? Where does that factor into it? But in the end, whenever you start mixing and matching, you're going to have to break out the calculator and start subtracting and figure out what you're going to you have to type into the router at that point. I think the three vendors here listed here, so I think in Junos, iOS XR, as well as the Alcatel boxes, when they refer to MTU, they typically mean what's actually the entire Ethernet frame altogether, end to end. But I think there's some discrepancy regarding FCS on specific platforms. But once again, there's no consistent approach that vendors take when it comes to actually specifying MTU. The other part is not all pieces of equipment could clearly do 8 to 9,000. Older equipment, older Cisco gear, some of the fast Ethernet port adapters, Engine 1, Engine 2 line cards. There's certain caveats of which ports can actually do it, which revisions of cards can do it. Older Juniper PICs, certain ones can do only 4500 for compatibility with other protocols such as Sonnet that might have been operating there. And some of the fast Ethernet PICs can only do a little bit above 1500 for any other additional encapsulation. And once again, changing any kind of MTU setting, depending on the equipment, but for the most part, just changing it is typically a traffic disrupting operation. As buffers are recarved and whatnot, it's something you can't just do without expecting some sort of loss. Here's just one picture of what it looks like from the end eyeball to content or wherever off in another service provider, and there's multiple locations within the network where MTU support, getting anything above 1500 may not be realistic for some time to come, all the way from the end host to the customer's CPE that they have. If it's on by default or if it isn't, does it make sense? Is it a low-speed link and it really buys the consumer nothing? For example, some of the other things are, the BRES, the customer's first layer 3 hop, does that support it? So even all the way to, which peers are going to support it, only some, a few. To see end-to-end, seeing 8,000 to 9,000 all the way through is probably not going to happen for still some amount of time. So one thing is, what actions would really be required to actually get this, down the path of where something will be better, where we can actually transmit 1,500 bytes without seeing fragmentation would be, does IEEE need to standardize on MTU value? And then at that point, all vendors can actually have a target to support, and maybe you don't need to manually type in the MTU or play subtraction to figure out what kind of interface on what kind of router, and just have all vendors kind of aim for the same target. Maybe that's one solution. Another item would be, it would be great if we have the ability to actually discover neighbor MTU. It doesn't seem that difficult. With some additions into ARP, maybe this could be done. Basically, it looks like all the mechanisms are there and can be done. The hardware support is there. That's something that would be great to actually consider. Another thing is, is there another option for path MTU discovery? Is there something else that could be implemented there that can basically detect when it runs into an MTU mismatch scenario and can react to that? And here's actually a pretty useful URL describing what are some of the jumbo frame equipment that can actually do jumbos and what type of frame and packet sizes that they're capable of, and across various vendors. It's pretty detailed and definitely worth a look. And that's about it.
You mentioned a better path MTU discovery. Has anyone ever thought of a system by which an end host can report back to the sending host that, hey, you just sent me a packet, but something in the middle fragmented it. The biggest frame, the biggest fragment was X size. Next packet, send that size, please.
So you'd want to have the destination host respond with something that, hey, I received your packet, but something was wrong. It was fragmented, or
yeah. I got the packet, but something in the middle fragmented it. And oh, by the way, the fragment size was X, and where X would probably wind up being the MTU of the path.
I think that's plausible. That's certainly worth an option for an alternative to MTU Discovery.
Okay.
Todd Underwood, Renaissance. So here's the cynical view. So you lay out all of these, a certain amount of benefits, but a large number of challenges. And a reasonable person could say, and therefore we're stuck with 1,500 bytes. There's no way you're going to manage to get all of these things ever upgraded to a reasonable higher capacity ever. What's your view on that? Is this really something, do you think that end-to-end or any reasonable amount of larger MTU is actually going to happen anytime soon anywhere?
I think the goal would be, right now since 1,500 is so commonplace, it'd be nice to at least support 1,500 across the internet. I mean, I think that would be a good thing to aim for, and with the amount of tunneling and different encapsulation that goes on within individual networks, whether it be labels or L2TP or whatnot, GRE, IP, that it would be really nice that if we had the extra buffer room. Intra-provider obviously is fairly easy, but I think inter-provider, I think it'd be nice to at least specify that this is my bare minimum of what I know what I can get, rather than sending IP packets out in the 1,400 range and just kind of crossing your fingers, I guess. I mean, I would like to think that it's feasible, but I think these are some hurdles that are going to stop it. So.
I think so.
Hey, Tom, thanks for compiling some of this, Danny McPherson. The only thing I wanted to mention actually was with the TCP PMTU stuff, or PMTU in general, the TCP maintenance working group in the IETF is doing a bit of work on that now. And one bug that we found in like TCP, for example, was where options weren't being calculated either inside or outside the conveyed MSS. And so things with MD5, for example, that considered that calculation versus a different stack that didn't consider that calculation would have different compute values for that. So anyway, the long and short of it is that TCP maintenance working group in the IETF is looking at some of this. So if folks are interested in contributing or conveying this kind of data, I think it's particularly useful. So thanks.
That's good to know. Thanks.
Kevin Oberman, ESNet. Might mention that almost every RNE network in the world today, that includes US, Asia, Europe, South America, almost all RNE networks these days run jumbo frames as a matter of course, routine, and it is expected to work. If it doesn't work, you get phone calls, complaints. And when I say jumbo frames, the standard size is settled on by a little-known group called the Joint Engineering Task Force, which is under the auspices of the Department of Defense, but in fact has almost nothing whatever to do with the Department of Defense, came up with a recommended jumbo frame size of 9,000 bytes several years ago, and the RNE community pretty much is universally standardized upon this. And it pretty much all works within the RNE community, and it pretty much, we assume, will never work outside the RNE community.
So it's always 9,000 payload, always? I mean,
the idea was to make sure that with all of the various overhead items, the headers, MPLS labels, VLAN tags, whatever, that we could be guaranteed of getting an 8 kilobyte actual data payload, as in fact was the example you gave in your slide, through from end to end. And therefore the inter-AS MTU should be specified as 9,000 bytes. Intra-AS is of course your own business, and in fact we run larger than that internally.
okay, that's great to know.
One thing to add, Daryl Newcomb with Calren, another RNE network. One of the operational constraints is how does when you have a boundary, you've got a big cloud of 9,000 byte IPMTU, then you have an edge that there's a campus network, the customer that's not going to support that. The device, that edge device, doing that fragmentation or sending back, how do they handle that fragmentation in a DOS or whatnot has been a pretty big, I don't think it was one of the items that you talked about, but that's been one of the big, kind of operational concerns in extending the 9,000 byte cloud to edges to places where it's more probable that there's going to be an MTU transition. If you're allowing garbage to come in and then transit across the network and hit an edge device that you're going to need to be either fragmenting or tossing ICMP exceptions to.
Is that a problem? I mean, is that occurring today to the point where someone's attacking it and it's just throwing it out and making that edge router punt it to CPU? I mean,
I've never had a whole chassis die from that, but yeah, we've had some challenges with it,
Okay.
but not very common. I mean, regular DOSes are more common. But yeah.
Okay.
Hi, Patrick Elmore, Akamai. It seems to me that if we do make the core, 9K or whatever, and then the end being either CPE at somebody's DSL modem or a random AS or leaf node that doesn't support more than 1500, then what we've really done is distribute the processing of this fragmentation down to the people who aren't with the program. And that's a good thing. If they do have problems like Daryl says and they get DOSed and it pegs their CPU, that's just more incentive for them to upgrade. And that doesn't mean that the core should not also upgrade at that time. If the people at the edge need to fragment, then it's their problem and their CPU is dealing with the fragmentation and everybody else is happy. So this sounds like a good thing to me and a nice, elegant, backward compatible upgrade path.
David Sin, Pacific Northwest Gigapop. I'll offer a counterpoint to Daryl's comment where we actually have had routers taken off the air because applications, uncompressed HD over IP, gig and a half, 9,000 byte packet, don't set the don't fragment bit, hits a 1500 byte link, kills routers at the edge of convention shows, kills routers at the edge of your R&D network, can cause problems occurring. So the edge is a really crunchy spot. The recommendation that we've made back to the people that are writing the software is set the don't frag bit so that the router drops it as opposed to drops in response as attempts to actually trying to fragment the packets.
Okay, so one thing I guess I'm always curious what kind of gear that was, and you can email me that if you would like. And then the other part would be, were the vendors did they offer any knobs regarding rate limiting of when these messages would it be encountered, or?
So that's also very platform dependent. Some of them do have some hardware-based rate limiters. A bunch of them have them software-based. So you're kind of in a catch-22 scenario.
Okay.
Hi, Richard Steenbergen, Inlayer, responsible for your inaccurate slide, one of them. So I guess the point to be made about fragmentation is why are you doing it at all? IPv6 doesn't support fragmentation for good reason. We've discovered at this point that when you're implementing hardware-based forwarding, you have a fast path and a slow path. You don't have a hardware-based solution to do fragmenting. People just don't do it, and that's why Path MTU Discovery, you're expected to set the don't fragment bit, and if you don't, you're going to black hole yourself. So that's the whole premise. So why even bother with fragmentation?
That's a good question.
Okay.